Slide. Okay, good morning, good afternoon, and good evening, everybody, depending on where you are. Obviously, this is a virtual conference, so you could be anywhere. My name is Jamie Coleman, and today I have my colleague with me, Richard Hagarty, and today we're going to be talking about some simple tweaks you can do to get the most out of your JVM. So let's get started. We've got quite a lot to cover in this session. Obviously, JVMs are huge, so you can talk about them forever. We're going to be looking at essentially what a JVM is and why it's important, how the cloud has changed the JVM over the years. We'll look at some of the different, the main JVMs that people use, things like HotSpot, OpenJ9, Growl, etc. We'll move on to picking the right runtime and why that is important. Then this is where Richard will take over. He'll talk about JVM. He'll talk about OpenJ9 class cache, what that is, and hopefully if we have time, a demo, a little bit on idle tuning and the JIT server, and then some new technologies that might come and help us in the future, and then a small recap with some links at the end to some of our content. So let's get started. So why is the JVM important? Well, firstly, without it, we wouldn't have Java today, would we? So what is a JVM and what does it do? So a JVM stands for Java Virtual Machine, which you all probably know, and it's essentially responsible for taking your application bytecode and converting it into machine's language for execution. So most other languages compile code for a specific system, but in Java, the compiler converts code for the Java Virtual Machine, and that can be used on any system, hence the phrase in Java, write once and run anywhere. So why do people still use JVMs? Obviously, Java's been around for quite a long time now. Well, first of all, like I mentioned, it's cross-platform. We can pretty much run Java on any machine out there, from Arduino, Raspberry Pis, all the way up to massive mainframes. It has a large library ecosystem. Obviously, it's been around for a long time, and with things like Maven Central and all these different dependencies we can pull from everywhere and all these open source projects, it has a really, really good library ecosystem. It has a great garbage collector, so clearing up all the rubbish as it goes along, just so you're not using more memory than you need to be. There are some powerful monitoring tools with Java, and we'll look at a few of those later on in the session. And it's proven and robust. It's been used by some of the biggest enterprises around the world for over 25 years, and we know it works. It runs on millions and millions of devices around the world. And we know we can trust Java. So I'm not a JVM expert. I'm not going to sit here and claim to be. This is a talk that interested me quite a while back, being a Java developer and using JVMs my whole career. I kind of wanted to understand how they work. So I started looking into researching this talk and basically just kind of understanding what's going on when we're writing our code, we're compiling it, and when we're running it. So essentially, you have three different parts of the JVM architecture. You have the ClassLoader Subsystem, which is responsible for loading, linking, and initialization. You have the runtime data area. And then, of course, you have the execution engine, which executes your code. So I'm going to give you very, very brief overview of what these different areas of the JVM do. So like I mentioned, the ClassLoader Subsystem, responsible for loading, so loads classes using three different class loaders. You've got Bootstrap, Extension, and the application class loader. The linking part essentially verifies the generated bytecode, prepares all the static variables, and then assigns values and resolves any symbolic memory references. And then initialization essentially assigns static variables with their original values and executes the static block. So that's the ClassLoader Subsystem. Then we move on to the runtime data area, the second part of the JVM. And this has things like your method area, which stores metadata and code for your methods. You have your heap, which is a common memory shared between multiple threads. It stores things like objects, instant variables, and arrays. You have your JVM language stack. This is created when a thread is created, and this stores local variables. You have your PC registers. Every thread has its own register, and this stores the address of the current Java virtual machine, which is being executed. And then you have the native method stack, and this holds native method information. So for every thread that's created, essentially a native method stack is also created. And then finally moving on to the execution engine. So it reads bytecode and executes it either using the interpreter or the JIT compiler. We'll talk a little bit about what the difference is between those later. We're going to talk, so it also has a native method interface, the JNI, and this interacts with native method libraries to provide the required libraries for the execution engine. And then, of course, the native method libraries, and this is a collection of all the native libraries we have in Java. So there's a little overview of the JVM, what it is, a little bit of how it works, without going into too much detail, because again, I could spend a whole session just talking about that. But now I'm going to move on to how the JVM has changed over the years. So compared to a JVM we had 25 years ago to a JVM we have now. And the main thing is money. It's always money that makes the world turn around and things progress. So for example, now we have to think about the clouds. We're essentially renting a lot of our hardware these days. So that's when the money kind of comes into things. So yeah, we need to basically save as much CPU and RAM, etc., as possible. And I like to always think about this, not as in terms of money, because as just normal developers, we're abstracted away from some of the cloud costs or the hardware costs that we're utilizing. But if you think about it as energy, that's a good way that I can kind of put it close to my heart, because essentially any money we're saving on the cloud, the more efficient our applications are, the more energy we're saving. With data centers, most of their costs, once they're set up, is pretty much supplying energy for the machines they're running. So imagine this is our application, we're running in our local data center. Of course, we always have peaks in demand, etc. But we have to rent the hardware or own the hardware to handle all those demands at any time of the year, right? Whereas now we move to the cloud or rented hardware, we can start freeing up more of that hardware we're not using, hopefully saving us less money, saving us more money, sorry. Freeing up this hardware, so we're not just locking it in and it's not being utilized, and then other people around the world can use it, and this will make everything a lot more efficient. But then, of course, we move to more things like microservices and functions as a service, etc., and then we have more granular control over essentially our applications and our hardware, so we can save even more money. So that's all great, but there's a bit of an overhead with the JVM, and I've always found this because JVMs traditionally are quite big. They're built to handle multiple applications and have a really high throughput and be robust. But when we move it to kind of a microservice architecture, we've got this big overhead that we're sticking in every single microservice. And that's a bit of a problem. So a lot of the people that basically create these JVMs and modify them, they've had to think long and hard about finding the right metrics for the JVM. And the key metrics we want to look at generally with a JVM are things like startup time, ramp up time, memory footprint, response time, CPU and throughput. But making changes to your JVM to make the startup time quicker might have detrimental effects, say on CPU usage or response time or footprint. So getting the right balance on a JVM to get these characteristics we need for kind of essentially microservices or very small services is a tricky one. So I would ask you to all put your hands up so I could see, but obviously it's a virtual conference, so I can't. I presume most people here had one of these phones. They're amazing phones. Remember, the batteries used to last about a week. I think Nokia have actually created a new phone where the battery lasts about a week as well, which is quite cool. But these basically were running Java ME. And Java ME was built for very small pieces of hardware and the requirements for things like small footprint, because again, these devices had very small RAM or hardly any RAM and usually more ROM. We needed fast startup because you didn't, for example, you start Snake on your old Nokia phone, you don't want it to take 5 minutes before it stops juddering. You want it to be working straight away. And quick immediate ramp up time as well. So the game shouldn't get better the longer you play. It should just work from the get-go. So these were kind of the requirements of Java ME on these devices. If we compare the kind of same requirements that we have in the cloud, they're pretty similar. So we want a small footprint, fast startup, and immediate ramp up. Now, the difference here was the hardware back then was limited by the technology we had. Whereas now with the cloud, we pretty much have unlimited resources, but we don't have unlimited money. So it's more the money side of things now that are shaping the requirements we have on the cloud, let's say. So again, back to kind of my other point and something I like to talk about, which is kind of why I've winged it into this presentation. So why should us developers care about optimizing our applications? I mean, it doesn't save us that much money. But if we put into consideration all the technology we're using around the world, There's over 500,000 data centers worldwide. The land they consume is around the same as 6,000 football pitches. So for Rich, who's from Texas, that's soccer pitches, I will say. And this was taken quite a few years ago, and they equal the same energy consumption of the whole of the United Kingdom times that 1.5. And that is the current energy consumption of these data centers, which we don't see, the public don't see. You know, it's all very good, they use Facebook, etc. But behind the scenes, there is humongous data centers sucking in loads and loads of energy. And as developers, we're the engineers of the world. So we're the ones responsible for trying to help solve these problems. Now, luckily, the hardware developers have come to the rescue, because without them, as you can see, without the hardware advancements we've had, we'd be using a lot more energy today in our data centers than we currently do. But the hardware engineers have worked very, very hard to make the hardware as efficient as possible. Now, that can't happen forever. We know Moore's law and things like that don't work as well these days. So now it's more for us as software engineers, etc., the developers, to do our part and make our applications efficient running on these pieces of hardware. Because it's very easy to build an inefficient application and just say it runs, it does the job, without thinking about the other side effects. Right, so there's lots of different JVMs available. Yes, you do have a choice, and there's pretty much a JVM for everything these days. There's some great named ones like Wonka, VM, etc. So yeah, just have a look. It just depends on what you're building. There's JVMs that are built for IoT devices, JVM literally built for robotics for Lego, which is cool. There's also the Maxine JVM there, which is basically what GraalVM has become these days. And that was created at Manchester University in the UK, actually. And there's one called Juice, etc. So there's lots of different JVMs. So you need to kind of look at what you're trying to build and then find a JVM which has the characteristics you need, because lots of different JVMs, again, are all tweaking them in different ways to try and get the best characteristics for their users. So the most popular JVMs, which we all probably know, being the Java Conference, of course, Oracle, HotSpot JDK. You've got the Adoptium JDK. There's the OpenJDK via Oracle. There's the Amazon Corretto one, Azul, Graal, and of course Eclipse OpenJ9 via IBM Semeru Runtimes. So there's lots of different JVMs, and I'd say these are probably the most popular JVMs that are out there. I've picked 3. So I've picked HotSpot, I've picked OpenJ9 because it has some differences to HotSpot, and then GraalVM because that is quite drastically different to the other 2, if you can call it a JVM. So a bit of an overview of HotSpot, a little history lesson for those who don't know, formerly known as the Java Hotspot Performance Engine, which was a bit of a mouthful, hence why they changed it to HotSpot. This was released in 1999. And this became the default Sun, which is now Oracle JVM in Java 1.3. Now, in November 2006, the HotSpot JVM and the Java Development Kit, the JDK, became open source. And this really paved the way for OpenJDK and many other JVM implementations out there. So thank you for that. HotSpot continuously analyzes, this is kind of how it works, and this is what I quoted from Wikipedia, but HotSpot continuously analyzes the program's performance for hotspots, which are executed often or repeatedly. These are the ones that are targeted for optimization, leading to high performance execution, which is why it's called HotSpot. So on to OpenJ9. So this JVM has a bit more place in my heart. Obviously, this used to be IBM's JVM before it was open source to the world. And this was kind of really designed to span all different IBM products. So things that work on a mainframe down to PowerPC, down to very small devices. So it was really built to span the kind of every usage you can think. It can go from small to large, so there's small versions of this JVM and bigger versions depending on your needs. It's really good at handling constrained environments, and Rich will talk a little bit about that later. But for example, if you've got a container and you don't have much memory in there, or you've got a memory leak, it can still, manage to keep the throughput going as opposed to just falling over. And it's been used by some of the largest enterprises on the planet. So it's now completely free and open source. So do check it out. It's very easy if you're using containers to switch JVM, and then you can just check the performance benefits you get depending on your application. But this is an overview of some of the performance specs with OpenJ9 compared to HotSpot. This was taken from the OpenJ9 website. So things like much faster startup time, a smaller footprint on startup, A faster ramp-up time, because again, the time your JVM takes to ramp up, your application takes to ramp up, is completely wasted resources, essentially. And a smaller footprint while it's under load. So moving on to Graal VM. So this is quite a new addition, I would say, to kind of the Java world. It was originally released in May 2019. It's based on the HotSpot OpenJDK with roots in the Maxine virtual machine developed by Sun, like I mentioned earlier, and the University of Manchester. Essentially, it was created, the Maxine JVM was created quite a long time ago, but there wasn't really a good enough use case for developing it into what Graal is today. Because we weren't using the cloud. There was lots of just factors. We weren't using microservices, but now it made more sense to actually utilize this technology. And so why is this JVM a little bit different, or why is this specifically different to JVMs? Well, basically it has a new JIT compiler for Java, the Graal VM compiler, and it allows ahead of time compilation of Java applications with the Graal VM native image. So you can compile all this stuff ahead of time, which is great. The Truffle programming language implementation framework and the Graal VM SDK enable different programming languages as well. And it can also handle things like JavaScript, so that's very cool. So the goals of this project were really to improve the performance of Java virtual machine-based languages to match performance of native languages. It was also to reduce the startup time of JVM-based applications by compiling them ahead of time. To enable things like Graal VM integration with Oracle database and all different databases, Node.js, Android, etc. Mixing code in polyglot programming languages, because it doesn't always make sense to use the same language for every project you're doing. There are lots of languages that are more suited for different applications, so it allows you to use lots of different languages. And it includes loads of different polyglot programming tools. So that was kind of the main project goals for Graal VM. Now, of course, there are disadvantages. Compiling ahead of time does have detrimental effects on things like throughput, but we'll talk a little bit about that later. So picking the right runtime. So, we could pick the best JVM, we could tweak it, we could have, a really efficient application. But if we're using the wrong runtime for that, then all of that kind of goes out the window, really, because out of the stack, the runtime is a very big part of it. So I'm going to talk about one of IBM's open source runtimes, OpenLiberty. We've just had our 5th anniversary birthday. I think it was yesterday or it was sometime this week. I can't remember exactly when. But yeah, so this was open sourced about 5 years ago with the IBM JVM, which now became OpenJ9. And this was one of IBM's biggest open source contributions in history. And Liberty has kind of these different project goals. So it really wanted to focus on being developer friendly, being just enough runtime so it's modular, you add in the functionality you need. Dev mode allows you to start the runtime and as a developer not have to care about it, not have to restart it. It'll just pick up any test changes, configuration or code changes straight away. Supporting the industry standards, things like Jakarta E, Java E, microprofile, and even Spring. And zero migration. So that is being key at the heart of Liberty, is being able to move your application and your code to the latest version of a runtime and nothing break. And because back in the day, that used to fill teams with dread, quoting a blog that we contributed on the other day. And yeah, I mean, it could take a lot of resources to move up, test your application, things would be deprecated and they won't work anymore. So that has really been at the heart of Liberty, because at the end of the day, we want developers to be using the latest and greatest. It was really designed for the cloud. Liberty came around when the cloud has just started to be established, so it was really focused on that. It was one of the first products in IBM to be containerized, and that's one of the first jobs I did. It's designed for DevOps. It's got a really small disk footprint on the cloud, really efficient memory usage, really fast startup, so you can start up in around a second, and with some new technology, even better than that. It's got really high throughput, especially with Spring. So if you swap out Tomcat for Spring, for example, do test out OpenLiberty because it has really, really great throughput there. And it has its own self-tuning thread pool. And like I mentioned, it is a just enough runtime. So we don't want runtimes that are 2-3 gigabytes in size when our application is, say, 100 megabytes in size. So really, we just want the smallest layer that it can run the application and do the job it needs to do. And that's what OpenLiberty does. Like I mentioned, we have a broad spectrum of support, and we've always tried to be the first to certify for a lot of these new industry standards like Jakarta EE 8 and 9. For example, first to deliver microprofile 1, 2, 3, 4.1, and 5, because we want people to use the latest and greatest technology as soon as possible. Now, I can't talk about OpenLiberty and not briefly mention Quarkus. So Quarkus is another runtime offered by Red Hat. And this is very similar kind of project goals to OpenLiberty. So unified configuration, zero config, so live reload like we have in dev mode. But this supports things like native execution. So you can use the Graal VM for Quarkus. Now, like I mentioned, there are pros and cons of doing that. So just make sure you pick the right runtime for what you need, because Quarkus using Graal it may give you the startup time you need, but if you don't need, sub-second startup time, that's when you need to think, okay, is this really the right technology for me? But if it is, you're using things like functions as a service, etc., this is a really great runtime for that. And of course, there's lots of other runtimes you can pick from. So just do your research, figure out the correct runtime or the one that most suits your project, because obviously that's a big part of your stack, and you don't want a big overhead there. So with that, I will now hand over to my amazing colleague, Rich. He's going to go through some of the things you can do to tweak your JVM. And like I said, hopefully, if we have time, give you a little demo of some of the OpenJ9 technologies. So with that, Rich, I will hand it over to you.
All right. Thank you, Jamie. Do you see my screen?
I do, yes.
All right. Switching over is a little bit difficult here, clumsy. Let me just get my thing set up. Get my pointer going. I like to use a pointer. All right. So the rest of this presentation is about making your Java code run more efficiently. Let's see if my pointer is not working. All right. It's going to make it a little difficult here. So here are some basic ideas on how to get the most out of your JVM. So one, the most important goal for all developers is should be writing efficient code. So it seems pretty obvious, but we can discuss some things here. We'll talk a little bit about that. Two, picking the right JVM, looking for the characteristics that are best fit for your application. And three, just like the JVM, you also want to pick the most appropriate runtime. For example, you don't want to run a bloated runtime for a microservice. Four, using profiling. We'll take a look at this in a little bit. And five, tweaking your JVM. So we'll take a look at some of the other options to make your JVM even more efficient. And remember, these needs can be different depending on your environment. For example, whether you're in development or production mode or running locally versus in a container. So now let's discuss each one of these a little bit more in detail. So number one, writing efficient code. So there's a lot of information out there on doing this, but here are a couple of ideas or some easy ones, some quick wins. Always use primitives when possible. For example, use lowercase int instead of uppercase integer, which is just a class wrapper. So this allows your JVM to store the values in the stack instead of the heap, which saves on memory consumption. Use string builder instead of string buffer when programmatically building your strings. String builder is a lot more efficient, I'm sorry. But keep in mind, it's not thread safe like string buffer, which so you may still need to use that. Avoid using iterators, which are very resource heavy, and avoid using big integer, big decimal classes like that. This one's fairly obvious. Don't allocate additional memory if you don't need to. Let's see, hold on, I'm sorry. All right, next screen. So number two, picking the right JVM. So remember, there are a lot of JVMs out there to pick from. So as we mentioned, there are a number of open JDK vendor sites where you can get their distributions. So Eclipse Adoptium is the keeper of the open JDK binaries, and they have a marketplace, which we're looking at here, where you can get some of the more popular distributions. So here's an example of what you'll see if you go to the Adoptio Marketplace website. You can select your vendor of choice, operating system, architecture, Java version, kind of one-stop shopping. And if you look closely, I've selected the IBM distribution. You'll see that the distribution is named Semeru Runtimes. So I do want to go over quickly what that is. And if you aren't familiar, it's the IBM's open source distribution of the OpenJDK. And it comes with the Eclipse Open J9 JVM, which Jamie discussed a little bit about. So in fact, it's the only OpenJDK distribution that does include the OpenJ9 JVM. So the name Semeru comes from the name of the largest mountain on the island of Java. So like the mountain that is taller than the clouds, their slogan is the part of Java that's really in the clouds. So kind of a clever little slogan. It comes in two flavors, has an open and a certified edition, the difference being the licensing and the supported platforms. So you can download both versions for free from the Semeru download page, which I have a link to here. And for containers, you can get images from Docker Hub, IBM Container Registry, and from Red Hat. Also, as we showed earlier, it is available on the Adoptio Marketplace, but just to let you know, from here, this site, you can only get the certified edition. So let's go back to our list. So number 3 is picking the right runtime for your application. So how do we decide? So here's a graph that shows some popular runtimes and where they fit best based on architectural style and API needs of your application. So, and notice there is some overlap here. So on the left, we see the WebSphere application server. So WAS is a great runtime with a long history of running monolithic applications. It's used by a huge number of Fortune 500 companies to run their enterprise software, but it's very big. It's around 4 gigabytes, and it takes around takes 10 minutes or more to start. Probably not very appropriate for microservices. So for applications developed to be more cloud native, or if you're migrating your monolith to a more cloud native approach, OpenLiberty is a great choice. As we mentioned earlier, it has a just enough size runtime. So size can be very small and startup time could be in the seconds. So this is a very good fit for microservices. But it can scale in both directions. So OpenLiberty can also handle monoliths or macro services. And if you're not familiar with that term, basically it's that gray area during transition when you're converting from a monolith to a microservice architecture, where you may have some services that are just too tightly coupled to separate completely. So you keep them together, and that's where that term comes from. And to the far right, we see Quarkus, which is a runtime specifically designed for microservice architecture. So it's great for things like functions or serverless. So let's talk about profiling. So there have been some great strides made with profilers, and it can be really useful to monitor all of your Java bytecode and the operations inside of your JVM. So they're great for isolating and diagnosing any bottlenecks or issues you may run into. So here's a list of some of the more popular profilers. So if profilers are new to you, you'll be amazed at what some of the detail they provide. If nothing else, you'll get a really good idea of how JVMs operate, and it's going to make you a better developer. So definitely worth your time to see what's going on under the covers of your JVM. So last, let's get to some tweaks to your JVM. And these are things you can do to affect the JVM that you've picked, right? In this case, we're going to show some features of OpenJ9, but in general, here's some ideas. Tuning your garbage collector. So there's lots of ways to do this that make your code more efficient. You can use the ahead of time compiler to improve the performance of your application, especially during startup time. And then we're going to talk about enabling class data sharing. So this is a feature of both HotSpot and OpenJ9. Hopefully I'll be able to demo this in a bit. Enable idle tuning. So this is a new technology that deallocates resources from your JVM when it's not being used, basically when it goes idle or in sleep mode. Then we're going to talk about a new technology in the OpenJ9 JVM called JIT server. So it's basically a JIT as a service running remotely from your JVM. So it's basically a service on the cloud or in a separate container. And heap size, we'll talk about this briefly. We recommend always starting with a small heap size, as small as possible, and grow as needed. So you'll run some various tests with different test loads to really fine tune this value because you really want this as small as possible. So let's dig a little deeper into a couple of these. So first off is class data sharing to help with startup times specifically. And we're going to be looking at how the OpenJ9 provides this. So what is class sharing? So it's basically shared memory, which means multiple JVMs can use it. And it's persistent, so it sticks around even if the JVMs go away. You can specify a size for your cache, but it can't be increased. If you ever do reach that limit, it just stops caching any more data. So when this is turned on, AOT is automatically enabled. So that means your shared class cache data will actually be compiled code. So this is where it really helps with startup times. So how does it work? Basically at startup, the JVM needs to load classes to be executed. So remember we talked about this, or Jamie did when we discussed the ClassLoader subsystem. So under normal conditions, the JVM looks for classes in this order, their own class loader, their parent, and then finally the file system. So when we use the class sharing feature, you can see that the JVM has an extra step where it looks in the shared class cache. So if it finds it there, it can avoid having to retrieve it from the file system. Again, this is where it makes up all the efficiency for during startup. So setting up the class cache is pretty straightforward. It's all done using JVM options. Here we see the X share classes tag. That's how you turn it on. You can actually specify a name if you want to share between multiple JVMs. You can set the size, but you can never grow that size after it's set. And obviously, if you're accessing a cache that already exists, you're going to get that one. It's not going to change that size. And then just a real quick note, if you use this in a container environment, you'll have to set up a Docker volume and then access it from your container. So I do have multiple slides here showing how fast and wonderful it is, but let me just go to the demo. We can do it in real time. So let me end my show real quick. Can everyone still see my screen?
Yep, you're all good, Rich.
Okay, good. So I'm bringing up the one of the Open Liberty guides. Let me go to the opening page. This is really cool. This is on the Open Liberty IO guides website, where we have a list of different applications you could try, or different. So this is for building cloud native applications. So we have a lot of sample code here that you can run through to learn different aspects of doing things with your cloud native application. And the beauty of this is you can run this in the cloud. So it's really cool. You don't have to download anything. And we're going to, this time here for this demo, create a RESTful web service. So there's instructions. You can learn all about all the steps required to do it. But we're going to jump right to, sorry, my screen is behind. Here we go. This is what happens when you start up your code sample. On the left is all the instructions step by step. You can simply click on the button and it'll actually execute that command in your terminal. We have an IDE here, full IDE. And again, I haven't downloaded anything. So we're going to go through this real quick. Let me go through the steps of I'm going to do a get clone to get the code. And now we're actually going to run it. So the first time it runs through, it's going to have to start the application server, then load our application. Hopefully this goes quick. And again, we're not using the shared class cache at the moment. So this is running normally.
So while we're waiting for that, Rich, there was a question about using class cache sharing with, so say if you're running multiple instances of containers of one Java application, can you use class cache sharing between multiple containers? I actually don't know.
I would assume so, but I haven't tried that.
So yeah, like Rich mentioned, you can mount in external volumes. You can put your shared class cache there, and then basically utilize that. So, in theory, yes, but I've never tried it, so it's quite interesting. I'd be intrigued to see if that would work.
So real quick, what I've done, I'm creating a new file, JVM options, where we're going to set up this shared class cache. But just to let you know, the last time we ran this, it took 9.6 seconds to load. So I'm going to add that parameter. Oops, can't type. And it automatically is saved. We click off, let's kill. I'm going to shut it down. We're going to restart it. Now, unfortunately, what happens, at least unfortunately for this demo, what's going to happen is that now it has this tag, so it's going to use that shared class cache, but it has to run through the startup of the application to load that cache. So we're going to have to do it one more time. It's going to build the cache, and then we'll see the benefits when we run it again for the third time.
So that should kind of answer the last question, which was, does the shared class cache notice code changes? Yes, every time you start up your application, it repopulates the shared class cache, so it will have a look. And once you've done that once, it just goes to those same classes. But if you do make a change to your application, it will then go and look for any new classes that have been changed, etc. And if they're ones that are required at startup, it will load them into the shared class cache.
Right. And I didn't catch the time. I think the last time it ran, it was 6 seconds. So now we'll run it with the cache. So this is where we'll see our improvement. We should have had some filler music or something. So here we go. There we go. So it finished, and it took 1.325 seconds. So a dramatic increase.
And just to clarify, like, imagine this is running on an online platform in the cloud built for, learning environments. So imagine if everyone made this change just by adding this functionality to their applications, going from 8 seconds down to 1.3 seconds. Imagine how much money and energy we could save on the cloud. So really amazing tweak there, done by the OpenJ9 team.
Yes, good point. So here are those slides I'm going to skip through that were showing the benefits of what we just saw. Let's see. There is this slide I do want to talk about real quick. So OpenLiberty does have an advantage over the other runtimes because of its direct relationship with OpenJ9. So remember, both are open source projects, but IBM is by far the biggest contributor and has put a lot of resources in advancing both of these technologies. So back in 2018, they set a goal to get startup times under a second by making enhancements to both the runtime and the JVM. So this goal was almost reached in 2020. Not sure where they are, but definitely the trend is going down. And that was the demo. Actually, here's a link to the demo I just ran. So you're free to run that on your own. So let's talk about idle tuning. from OpenJ9. So idle tuning essentially allows your JVMs to save some resources when it isn't servicing any requests. So let's take a look at a normal resource allocation without idle tuning. This slide shows the amount of memory used with various size containers. One using HotSpot. Is my cursor still on? I think so. I need to turn that back on. Sorry about that. So it shows HotSpot in red and OpenJ9 in blue. And as you can see, the amount of memory required by OpenJ9 is about half the size of when we get to a large container. So the bigger the container, the more the obvious advantage you get with OpenJ9. Because OpenJ9 does a great job of just returning memory back and after it completes tasks such as JIT compiling. And now we'll take a step further and we enable the idle tuning using this parameter here. As you can see, there's some idle periods shown in these red markings here, these span arrows. And notice that both the process memory and the Java heap flatten out during these idle times. So it's returning memory back using garbage collection. So that's so it's all about saving resources and energy, which Jamie really harped on. So next we're going to talk about the last of our JVM tweaks, which is the JIT server. This is another OpenJ9 technology. In fact, it's the only JVM that supports it. This is actually my favorite feature because it has a great impact on CPU throughput. It can really help out with memory issues in containers specifically. So as we mentioned, we can have a JIT server running remotely. This can be in its own container or as a remote service. Here we show multiple JIT servers handling JIT requests from multiple JVMs. Load balancing can be handled by the container orchestrator. And if you notice, the JVMs still have a JIT. We're crossing out the process that it's doing, but it still remains in the JVM. So the great benefit of the JIT server is that JVMs can continue to work even when under heavy loads or constrained environments like containers. So here we show three graphs. The red line is a normal OpenJ9 JVM, and the blue one is with the JIT server enabled. And as we move further right, the amount of memory allocated to the container grows smaller and smaller. So we're showing a more constrained environment the further we move to the right. So if we look at this chart here at the far right, you can see that the red JVM under normal conditions kind of hit its floor here with CPU throughput, whereas the blue one is acting like it has a lot more resources. And actually this is the case because it's offloaded all its compilations to the JIT server process. So this gets back to sizing containers. So with a JIT server, you no longer have to size your containers to handle the worst case scenario. So spikes in memory consumption and throughput are minimized, so you can size your container more appropriately. So in the world of containers, one of the main reasons for containers to crash is out of memory errors. So the JIT server definitely helps with all of this. So speaking of container size, here's a container density graph. So this is a great experiment they ran. So this was run on a Red Hat OpenShift instance running on AWS. So we had two test cases. Each could use up to 3 nodes, each with about 12 gigs of memory. So the goal of this test was to efficiently load and run 4 real-world applications, each replicated multiple times across each node. So the colors here represent the different applications, and the shape indicates the relative size of the container. So the top is the first case without running a JIT server. And as you can see, it requires 3 nodes to replicate all of the applications. The bottom row is the next test where we actually use a JIT server. And you can see the JIT server process here in brown. But notice that we can create the same amount of replications per application, add a JIT server to each of the nodes, and still only require 2 nodes. Also notice the shape of each application is smaller. This is because we don't have to size them to handle any out-of-memory crashes caused by the JIT compiling within the JVMs themselves. So the bottom line here is that we basically are running just as efficiently, have the same amount of resources, but saving 33% of the dollars. Whoops, go to the next slide. So how do you set up the JIT server? It's pretty straightforward, just with some more JVM command line options. So by the way, the JIT server is just another standard J9 JVM. It's just running under a different persona, and that's how you do that with the JIT server command. To access it, you just have to add the tag use JIT server. And so as I showed, you can drastically make your containers faster and much more efficient with very little effort. So now we've spent some time on some of the things that already exist. Let's talk about some future tech that's coming down the road. So one technology is gaining a lot of momentum and interest is Instant On. This is a JVM solution to help with quick startup. So this technology is all about reducing startup time for your Java applications. The concept of Instant On is taken from a feature in Linux called Cryu, which enables a snapshot taking of a running application which can then be restarted from that point. So the theory is that we're going to do the same thing with running applications or microservices. Once it's in a runnable state, we'll take a snapshot, and if it needs to be restarted, it can be done almost instantaneously. So this would be a huge improvement in a container world. And this, remember, this feature is only available if running OpenJ9 inside of OpenLiberty. Just a note, there are some other competing solutions based on this same Linux feature, but those are all proprietary. This is totally open source. Here's a graph showing the test results we've done, which would make a big difference in startup time. So here you see the time it takes to start 3 different applications and how long it takes to respond to that first request. So the blue bar is running these applications normally, and the red bar is with Instant On. So obviously, the bigger the application, the more dramatic the results are. And this feature is actually coming out, I think, next week. So look for that. It's called Instant On. So that concludes today's presentation. Let's do a quick recap. So the main theme is all about saving energy and resources. From a global perspective, every bit helps save the world's energy supply. And at the local level, we're saving energy to save our company money, right? So we learned some ways to do that. We write efficient code, do your part as a developer. We pick the right JVM and the runtime to best fit our application. If your code can run using less resources, take advantage of that. We learned a little bit about profiling and how it can find some bottlenecks or issues to make your code more efficient. And last, we talked about some advantages of utilizing your specific JVM with some options and features to improve the efficiency and reduce your resources. And we showed a bunch of features that are built into OpenJ9, which we definitely hope that you take a chance to explore on your own. At the very least, realize that there are many JVMs out there. Pick the right one for your needs. And always remember, you have a choice. So here are some links to all the information that we presented today. This includes links to JVM and runtime options that are available from the open source projects and vendors. We also have links to interesting articles that I think we touched on today. Most of these we touched on today. Oh, and I wanted to end with this. This slide just came out recently. There was a study, maybe some of you have seen this, that there was a study, I think, by a Portuguese group that tried to rate all the languages based on how they were at consuming energy. And Java actually made it in the top 5, which is pretty impressive. So anyway, that's an interesting, there's a link to the article there. So that concludes the presentation. So thank you very much. And do we have any time for questions?
Yes, moderator, do we have time for a few questions? Awesome.
Yeah, about 5 minutes if you want.
No worries. All right, I'll make this quick. So Derek basically asked, so you say don't use an iterator, but what would you use instead if you wanted to iterate through a collection and remove some elements? I kind of gave a brief explanation, Rich, which was, I would say, obviously there's times where you can't avoid using an iterator. So if you need to make changes to parts of your elements of, then it gets to the point where you kind of need to. But yeah, I'll let you try and answer that one, Rich.
No, I think that's perfectly right. Iterators are convenience. They're very nice to use, but they do have some background resources that are being used. And if you can go straight away at it, it's probably more efficient. And you know what? Efficiencies are built into Java itself. And so we were trying to pick some that they may be a little controversial or whatever, but I think in general, the other ones are probably a little more doable.
Yeah.
The iterator one's kind of doable. The iterator one's a little reaching, I think, but
yeah.
just to note.
There was one more question that I tried to answer, which was providing the JIT server is running on the same node. No, sorry. The question was how does network overhead affect JIT compilation time? I kind of just said that as long as it's running on the same node as hardware, it should not affect compilation time, but I've never ever tried to run it on a separate server or separate piece of hardware.
Yeah, that is a key point. That's a very interesting point. So the JIT server runs very well in certain environments. And if there's network latency at all, it really diminishes the effect that the JIT server has. So you have to keep that in mind. If you do some research on JIT server, where there's a lot of articles out there, that's one of the recommended use cases that you really have to have network connectivity. It has to be very quick because there is a lot of overhead involved with passing the requests back and forth between the JIT server and the JVM.
Awesome. I think that's it. I don't know if I've missed any. If I have missed anyone in the chat, feel free to re-put your questions there. I think I tried to answer most of them as we went along. Creating a custom JRE with JLink. I don't know anything about JLink, and I tried to have a quick look while Richard was talking. Rich, do you know much about JLink?
No, I do not.
No. Yeah, sorry.
Sorry.
Yeah, I literally just come across it because you mentioned it in the chat and I was like, oh, what's this? So yeah, I'm not actually sure. Yeah, I won't be able to answer your question. Sorry.
Yep.
Any other burning questions?
And you can reach out to us.
Yes.
We have our email addresses, Twitter accounts. We definitely want to hear from people. We like to engage the community. So any questions you have, please forward them.
And we are running a workshop tomorrow about, myself, Richard, and 2 of our colleagues will be running a workshop tomorrow as well. The workshop name is, we'll have it in my calendar. Venturing beyond 12 factors. So talking about some of the additional factors that have been introduced when creating cloud native applications. So if you're interested in that, come along to that. Or if you have any other questions about some of the stuff we talked about today, you want to ask, and you remember between now and tomorrow, feel free to join that session and ask there.
Yeah, in fact, the demo that I showed was using the guides that we'll be going through in the workshop too. So it's really good.